This video covers electric fields. Gauss's Law, Part 1. Now, in a previous video, we talked about the flux through a closed surface. We said that the flux through a closed surface is zero whenever the excess charges are found outside the closed surface. Now, this was true when the field was uniform, like in this first picture. When the field was non-uniform, like in this picture, and when we say it's non-uniform, that means it is stronger here, and we can tell by the density of the lines. We can see that they're closer together. And over here that they're further apart, so the electric field is weaker at this point. But because the area that it crosses through are proportional to the differences in electric field, then the electric flux was the same in both. So if the electric flux was the same in both, then they still canceled out to become zero. And then in the last example, even if the closed surface was unusual, so even if we had a picture like this, where it's not a spherical surface at all, the same number of electric field lines that go in are the same number of electric field lines that come out. So our flux is still equal to zero. Now we can look at new situations where the charge is actually inside of the closed surface rather than outside. Now, our electric flux would no longer be equal to zero. Now let's say that we have a positive charge here, and the electric field line from a positive particle or positive charge goes out in all directions. Okay, so the flux is going to be a positive flux. Again, it comes out of our closed surface. Again, these lines don't cancel out, so our flux will not be zero. It'll actually be a positive value here. But to calculate this flux, we want to now use our integral symbol, but we're actually going to use a very simplified version of it. Now, this is our equation for flux. This symbol right here just represents the integral symbol that's used for closed surfaces. So we're saying that this integral is taken about a closed surface, and in this case, we're looking at a sphere. Now, this point charge right in the center is a certain distance away from the edges of this sphere. Then the electric field is constant at all points along the edge of this sphere. So, if the electric field is constant, we can pull it out of the integral. Okay. Our change in area in this case is going to be 4 pi r squared. And this is the surface area of a sphere. So that's our change in area. You can see that this equation here is the equation for an electric field. So putting those two together, you see that the 4 pi's cancel out. The r squares also cancel out. And all you're left with is q over epsilon naught. So that means that we can simplify this equation of the integral to say that the flux is equal to q over epsilon naught. Now, you're going to see this equation different ways. The q might say in, as in the charge inside your Gaussian surface, and we'll talk about that later. Or it might say ENC, which means enclosed. Either one, all this is referring to is a charge inside of our surface, our closed surface. So we can summarize Gauss's law by saying that the net electric flux through any closed surface is given by this formula here in the center, where Q is the net charge enclosed by the surface. And we're going to look into different examples of that in a second. Now, charges outside the surface still generate no flux through a closed surface, okay, just like they did before. So again, charges outside the surface still generate no flux through a closed surface as the electric field lines enter and exit. That does not mean it doesn't have an effect on the electric field at the surface, but it does have no effect on the electric flux. And we'll see examples of that in class. Also, a net charge enclosed by a surface is the only way to generate a net or non-zero flux through the surface. So again, we need to have that net charged in order for us to have a non-zero flux. Now, although this equation shows the relationship between flux and charge enclosed, which we'll see in a bit, what this equation is actually mostly used for is to solve for the electric field at different points, which we'll see at the end of this presentation. In this example, we have a positive charge enclosed, so our flux is positive q over epsilon naught. In this example, we have a negative charge enclosed, so our flux is negative q over epsilon naught. Again, you can see that for a negative charge, that our electric field lines go into our surface. So when they go into the surface, remember it is a negative flux. So it works out here. Now think about when we have more than one charge. Here you see a positive charge and a negative charge. So inside of our surface, the net charge enclosed is 0. So there is 0 flux. What that means is there is the same number of electric field lines going into the surface as there are coming out of the surface. So the same number of electric field lines coming in as going out. So again, our flux would be equal to 0. In this example, we have the problem say, what is the net flux through the closed surface, the blue sphere, shown below? Here, our positive charges are going to be red, and our negative charges will be blue. So our flux, which is the integral of E with respect to A, which is also equal to the enclosed charge over epsilon naught. Okay, this is our flux equation. Again, our net enclosed charge is if we have 3 positive charges and 2 negative charges, then our net charge is a positive Q. Again, the net flux due to the charges outside of the surface is still 0. The charges outside don't matter. That means the net charge inside the surface determines the net electric flux through the surface. And this is true for any closed surface of any shape. Again, you saw that our r's cancel out, so it is independent of the shape of this sphere or this surface. So let's say we're trying to calculate the flux for these 3 different surfaces. Surface 1 is in red, 2 is in blue, and 3 is in green. Again, the flux is simply the charge enclosed divided by epsilon naught. Now the charge enclosed here, we have 2 positive Q plus a negative charge plus a negative charge. So we have 0 flux through surface 1. For the flux of surface 2, we have 2 negative charges and a positive charge. So our flux is a negative Q over epsilon naught. And the flux of our third surface is 3Q. We have 2 positive and another positive charge plus a negative charge. So we have 2Q epsilon naught. Again, all we're concerned about is the charge enclosed by the surface that we're trying to solve the flux for. Now, these closed surfaces that we were referring to are not physical surfaces. They're referred to as Gaussian surfaces. And Gaussian surfaces are imaginary areas generated in space to make analyzing imaginary lines, which are electric field lines, of invisible fields easier. It is a little bit like a test charge. Okay? It doesn't exist. We can put it wherever we want, and we use it to test a location in space for a field phenomenon. Again, what we're talking about are these closed surfaces, and they'll be referred to as Gaussian surfaces. So as an example, let's say you're asked to solve for the fields at a point P between 2 charged plates. Okay? We can figure out the direction of this field by using a test charge. So let's say we put a positive point charge in between these 2 plates into this electric field, and we figure out the direction that it is being forced. Okay? If we put a positive test charge, then the direction of the force is the direction of the electric field. So now we can figure out the direction of the electric field, and we can go from there. Then that's where the Gaussian surfaces come in. A Gaussian surface can be used to visualize the field strength. A Gaussian surface mimics the shape of the charged object. They are centered on the object that created the field. They also pass through a point we are interested in, and they are symmetrical. This part is very important. Then we can solve for the flux through the closed surface. Now, this part that says the Gaussian surfaces mimic the shape of the charged object, this means that for whatever Gaussian surface you're trying to create, you want it to mimic the electric field. Now, for the most part, you get to decide what your Gaussian surface is going to look like. But in some problems, you might actually be told what your Gaussian surface is, so you're going to have to work with that. But these problems don't come up as often. Again, because the Gaussian surfaces aren't real, you can use them as any which way that you'd like. The point of this, or the trick, is to employ them correctly in the right location with the correct geometry to help you solve these problems. So let's say you're looking at point charges, which are spheres. Then you're going to want to use a Gaussian surface that's a sphere. So we said at the beginning that although Gauss's law is written as a flux relationship, we actually really use the equation to solve for the electric field at different points. Now, here I have a point charge. What I'm going to do is create a Gaussian surface so I can figure out what the electric field is at point P. Now, this blue line right here is my Gaussian surface. I could have drawn this Gaussian surface at anywhere, but because I want to know the electric field at point P, I'm going to draw it so that it goes through the point P. Now, I also want to make sure that it's centered so that the electric field is the same at all points. If that wasn't true, then I wouldn't have my electric field be a constant, and so I'd have to pull it out of the equation. Okay? So it's very important that it's placed in the center so that the electric field is constant at all points along this line. So we don't have to do the integration. So again, if my electric field is constant, then I can pull it out, and it's going to look like E. Change A. My charge enclosed over epsilon naught. Now my charge enclosed is a positive Q, a positive proton. Remember that my electric field equation is KQ over R squared. And my area in this case is the surface area of a sphere. Even though that you only see a two-dimensional figure here, you still have to treat it like a three-dimensional figure. So again, my A is going to be 4 pi r squared. Okay? And this is going to be the area of my Gaussian surface. So actually, since we're trying to solve for the electric field, instead of putting it in like this, I'm going to leave it as E. And I'm going to try to solve for E. So that means my electric field at point P is Q over 4 pi r squared epsilon naught. Now, if you remember that K was actually equal to 1 over 4 pi epsilon naught, then I can make a substitution here. Where 1 over 4 pi epsilon naught is K. So you see that my electric field, some distance away from this point charge, comes out to the equation for an electric field. So we know that our process was correct. Now, this is a very simple integration or application of Gauss's law, but next time we're going to see a little bit more intense calculations. Now, before we can look at the more complicated examples, we need to look back at conductors and insulators. We said that there are two types of objects that can hold excess charge, conductors and insulators. First, we need to see how this excess charge is distributed in each case. Then we'll use the Gaussian surface to calculate and graph the electric field in and around spherical conductors and insulators. So we know from our first video in electrostatics that conductors allow electrons or charges to freely move around. Now this excess charges on a conductor repel each other along electric field lines. So what that means is that the excess charge piles up on a conductor's surface. meaning that once the charges are on the surface, the interior becomes neutral. There is no electric field inside a conductor. Again, this happens when excess charge is placed on a conductor. A way to help you remember that is think of what the electric field would be at point P. So from this charge, the top charge on the red circle, because it's a positive charge, the electric field lines go away from it. So at point P, from this charge 1, okay, it'll be going out in this direction. For charge 2, it'll be going out in this direction. Charge 3, here, 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 and here. Now these are all the electric field directions from these charges shown here. Now what you notice is because an electric field is a vector, all these vectors are going to cancel each other out. Remember that all of these charges are going to have the same charge, and they will all be the same distance away from the center. So there is no electric field inside of a conductor. Another way to think about it is the way we're just discussing Gaussian surface. Let's say I created a Gaussian surface in the center here. I am enclosing no charge, therefore there is no electric field. Remember, you do not have to be told about the charge distribution on a conductor. If the conductor has an excess charge, the charge must pile up on the surface of the conductor, meaning that there will be no electric field at the center. So this is where we're going to stop for now, and next time we're going to look at some graphs for a Gaussian surface, both a conductor and an insulator, and then look at some more integrations.